Welcome to section 5.3, special factoring methods. Alright, so we have a few different methods we're going to look at, and the first one is, I'd say very common in this course, would be something called the difference of squares. Well, the main thing to look at, the difference, we should think of subtraction. And then squares, well, we're thinking of items that are being squared, right? So for example, x squared minus y squared. This would be called a difference of squares, because there's a difference and both of the items are squares. Now, the special method for factoring this is x minus y, x plus y. So notice, it's the item before it was squared, and we have a plus and then a minus. So two different things, a plus and a minus. And these items here on this side, these two binomials are called conjugates. Conjugates of one another, because they have the same first terms and same last terms, but different signs. Okay, so let's take a look at actually factoring. So real quick, there is a typo. Go ahead, cross this one out. It should be 2x squared minus 8y to the 8th power. Alright, so first we're going to check for a greatest common factor. And since both of these two terms are even, we can go ahead and pull out a 2. So we have x squared minus y to the 8th. Oops, sorry, that should be a minus 4y to the 8th. After that, so notice we have a subtraction sign. This could possibly be a difference of squares if we can rewrite the first term and the second term as squares. Let's see, we have 2, and I'm going to go ahead and do this on the side. X squared is technically x squared, right? And then the 4, y to the 8th, can we write that as something squared? Yes, we can. We can write that as 2y to the 4th power, right? Because if we distributed the 2 to each of them, we would get 2 squared y to the 8th power. Okay, so we can rewrite each term as something squared. So we have x squared minus 2y to the 4th squared. And I'm going to go ahead and show this work on the side. You wouldn't usually need to show this, but because we're working on a new problem, I'll write a little more work. So we have x squared minus 2y to the 4th squared. Now, how does the rule work for factoring? Well, we take the unsquared version of each one and place them in the binomial. So let's go ahead and do that. So we have x, and then we're going to take the last one, 2y to the 4th, 2y to the 4th, and then put 1 plus and 1 minus. And we're done. Once again, note we input the unsquared item into the binomials. Alright, so let's go ahead and write that down. That was just the side scratch work. So we still have that 2 following along, and then we said x minus 2y to the 4th, and then x plus 2y to the 4th. Now, whenever I see a minus sign in a binomial, I might think it's a difference of squares. So I see that minus, however, this is not a square. That x is not a square, so we're done. Everything is factored. Let's take a look at the next one. Well, I see a minus sign, so this could possibly be a difference of squares. The question is, I have to figure out whether this first item is something squared and whether the last one is. Well, the last one, that's easy. That's just 1 squared, right? 1 squared is 1. Okay. But the first one, can I write this as something squared? I have to be creative here. 79 is 7 squared, and x plus 2 squared is just x plus 2 squared. So I can rewrite this as 7x plus 2 squared. Okay, so I'm going to go ahead and rewrite everything. So we figured out what these squares are of each item, or you could think of it as a square root. So I know that this is 7x plus 2, sorry for my dog barking in the back, squared minus 1 squared. So now we know the first item being squared and the second item being squared. So we can rewrite it as x and the x value, and then the y, the y and the y value. Let's go ahead and do that. So the first term is that huge x plus 2, and then we'll go ahead and do the minus and our last term. So that's the first binomial, the minus, and then we'll do the next one. 7x plus 2 And then finally we have the plus 1. But we have to simplify these two. Because we have that 7 in the parentheses, let's go ahead and distribute the 7. And we'll get 7x plus 14 minus 1 times 7x plus 14 plus 1. And then, let's see, simplifying, so let's go ahead and add the like terms. And what do we have? We have 7x plus 13 and 7x plus 15. And we're done. We have our two multiplication problems perfectly factored. So now, the next thing we have is the sum of squares. A little different, but a similar idea. We have a sum, which would be addition, right? And then of two items being squared. Now this one, in Math 103 or below, so any course below or Math 103, would be considered prime. We don't factor these. So, whenever you see something that's a sum of squares, you would say it's prime. It's not able to be factored. Alright, so you could go into that and you could try find a way to get that, but there is no way to get that with the numbers that we use in the classes below 103. So let's see the first one. A, we have a plus sign, and are each of the items squares? Well, that's a perfect square, x squared, and then we also know that 1 is a perfect square. So this is a sum of squares, which we know is prime. I don't have to worry trying to factor it. I already know it's prime. It's a sum of squares. Now let's take a look at the next one. B. Well, this one's a little weird. It's not a sum right now. There's still a minus sign there. But notice, I could actually factor out something from each of these. They both have a 5 in them. So let's go ahead and factor out that common factor of negative 5. And then I'm left with m squared plus 4. Ooh, and what do you know? This is a perfect square, and so is this. Oh, however, that's a plus sign. So we know that that, right there, that binomial, this is a sum of squares. So you might be tempted to say, well, then our answer must be prime, right? However, you have to be careful. We did actually manage to factor the original expression, right? We factored out the 5. So we wouldn't write prime for this. Even though there is a sum of squares, we still managed to factor the original one. Alrighty, so that would be our answer. Let's go ahead and box that. Alright, moving on. So factoring perfect square trinomials. What are perfect square trinomials? Well, basically, if we have something, so this is the generic form. Once again, you can read these in your book, in the section, when you're reading the section for this week's. So if you have x squared plus 2xy plus y squared, it factors perfectly into the exact same binomials. Notice these two are not conjugates. They have the same sign on the inside. And then we can rewrite this as x minus y squared. So that's the positive version. I didn't exactly leave a whole ton of room for this, so let me go ahead and move it over here, and then I'll rewrite the other one above it in a different color. Did not use room that wisely. Actually, let me go ahead. Okay. So that was the plus version, and then we also have the negative version. If we have x squared minus 2xy plus y squared, we can factor that perfectly into the exact two terms x minus y, which we can rewrite as x minus y squared. Now, how can we identify these? That's the main thing. Well, if you'll notice, on both of them, if we have one term on the beginning and then the one term in the end, the middle term is that first term times the last term and then multiplied by 2. And that happens for the other one. Now, this is just a pattern that some mathematician noticed with certain trinomials and decided to call it the perfect square trinomials. Okay, I usually don't often have this happen when I'm factoring, but it's just a special method. So let's take a look at example 3. Factor p squared minus 8p plus 64. There is a small typo in this, and hopefully I fixed the typos that are appearing on this before you guys get the notes. So this is p squared minus 16p plus 64. Alright, how would I know if this is a perfect square trinomial or not? Well, the main things we look for are, 1, that the first item is a perfect square and that the last term is also a perfect square. Well, the first one, the first term, it's easy to tell that that's a perfect square because that's already p squared, right? But the last one is a little harder. Is 64 something squared? It is. It's 8 squared, right? So I can go ahead and rewrite this as p squared minus 16p plus 8 squared. So that was the first test, to make sure the first term and the second term were perfect squares. The next thing to see is the middle term 2 times the first term times the last term. And not the actual squares in the terms, the square roots of the terms. So let's see, is it the same? Well, we have 16p. It is. Alright, so we proved that it is a perfect square trinomial. Alright, so let's go ahead, and that means we can rewrite this as the first term, which we found out was p, and then the second term, which we found out was 8. So we can rewrite it as p, oh, and careful, we're working with the negative version. So it means we had two negatives. So it's going to be p minus the second term, which is 8, and then p minus the second term. We go ahead, that should be a minus sign. And then minus the second term as well. They are going to be identical. Okay, so it's different than the difference of squares. These guys end up factoring as identical binomials. So since they factor as identical binomials, we can rewrite it as p minus 8 squared, because there were two of them. 1, 2 gives me that squared. Alright, and to check our answer, we could go ahead and FOIL. You don't need to check your answer, but if you want to, always remember you can FOIL. First, outside, inside, and last. And that does indeed give us the p squared minus 16p plus 64. Awesome. Alright, so once again, this one doesn't show up that often, but if you want to go ahead and memorize the formula for it, you can. It's usually not something that I see applied that much. Just a good way to practice factoring. Alright, that is it for this section. If you have any questions, once again, drop by my office hours.